Today, we'll be diving into the topic of designing sequential logic circuits. This is a fundamental area in digital electronics, where the output depends not only on the current inputs, but also on the past sequence of inputs, meaning the circuit has memory. My name is Earl Albert, and I'll be guiding you through the concepts, tools, and techniques necessary to design these types of circuits effectively. As we progress, we'll explore the principles behind sequential logic and look at practical examples to solidify your understanding. Let's take a closer look at the syllabus for this course. We'll start by exploring various types of latches and registers, both static and dynamic, which are fundamental building blocks in digital circuits. We'll also dive into pulse registers and sense amplifier-based registers, which are crucial for efficient data storage and transfer. Pipelining is another key topic, helping us understand how to improve performance by overlapping operations. We'll cover Schmitt triggers, which are important for noise immunity, followed by monostable and astable sequential circuits, explaining their behavior and applications. Finally, we'll address timing issues, including the timing classification of digital systems and synchronous design principles, which are essential for ensuring that our digital circuits operate reliably and accurately. On this slide, I'll give you an overview of the key topics we'll cover in this module. We'll start by exploring static latches and registers, which are fundamental building blocks in digital systems used for storing data reliably. Then, we'll look at dynamic latches and registers, which operate differently by temporarily holding data and require careful timing to function correctly. After that, we'll dive into pipelining, a crucial technique to improve the speed and efficiency of digital circuits by overlapping operations. We'll also discuss the timing classification of digital systems, helping us understand how different systems manage time constraints and synchronization. Finally, we'll wrap up with synchronous design principles, focusing on how clocks coordinate operations to ensure systems function smoothly and predictably. These topics form the backbone of designing efficient and reliable digital circuits. Here, we're looking at sequential logic, which is fundamental in VLSI design. Sequential logic circuits rely on two main storage mechanisms. The first is positive feedback, where the output is fed back into the input to maintain a state. The second mechanism is charge-based storage, which involves storing information as electric charge, typical in devices like capacitors. Understanding these storage methods is crucial because they allow circuits to remember past inputs, enabling the creation of complex and reliable digital systems. Here we are looking at two fundamental types of data storage elements in VLSI design: latches and registers. First, let's talk about latches. A latch is level sensitive, meaning it stores data whenever the clock signal is high. So as long as the clock is at a high level, the latch continuously updates its output to follow the input. On the other hand, registers are edge-triggered devices. They store data only at the moment when the clock signal transitions, either on the rising edge or the falling edge. This edge triggering makes registers more precise in terms of timing because they capture and hold the data at a specific instant rather than during an extended clock period. The diagrams show the basic input-output relationship, where D represents the data input, CLK stands for the clock signal, and Q is the output. Understanding the difference between level-sensitive latches and edge-triggered registers is crucial for designing reliable synchronous circuits, as it affects timing, control, and overall circuit behavior. Now let's talk about static latches and registers. These are fundamental components in digital circuits used to store data. A static latch holds its output steady as long as the enable signal is active, making it useful for temporary storage. Registers, on the other hand, consist of multiple latches and are designed to store several bits of data simultaneously. They are essential for buffering and synchronizing data in a system. Understanding how these elements work helps us grasp how information flows and is maintained within digital systems. Here, we're looking at the bistability principle as it applies to a latch. A latch is a bistable device, meaning it has two stable states, either 0 or 1. This is fundamental in digital circuits because it allows the latch to store a bit of information. The slide shows a simple static latch model made from two cascaded inverters. Notice how the input VI2 equals the output VO1, and input VI1 equals output VO2. These two inverters feed back into each other, creating a stable loop that maintains the state until an input change occurs. The voltage transfer characteristics illustrate how the latch switches between these two states, reinforcing the bistable nature of the device. This principle is crucial in VLSI design, where reliable memory elements are essential. Let's take a closer look at multiplexer-based latches. These latches use a multiplexer controlled by the clock signal to determine when data is transparent or latched. There are two main types, the negative latch and the positive latch. The negative latch is transparent when the clock, or CLK, is low, meaning that when CLK equals 0, the input data passes through directly to the output. On the other hand, the positive latch is transparent when the CLK is high. So when CLK equals 1, the output follows the input. Understanding this transparency behavior is crucial because it affects how data flows through the latch and is stored. The inputs are labeled as D for data, CLK for the clock signal, and the output is Q, which holds the latched value until the latch becomes transparent again. This concept is fundamental in VLSI design, as it helps manage timing and data storage effectively in integrated circuits. Here we have a mux-based latch implemented using transmission gates, which are labeled as TG1 and TG2. The operation of this latch depends on the clock signal. When the clock is high, TG2 is activated and TG1 is turned off. This switches the latch so that the input D is directly passed to the output Q. On the other hand, when the clock is low, TG1 turns on and TG2 turns off. This closes the feedback loop, allowing the output to retain its previous value. This mechanism is fundamental in VLSI design for storing data temporarily, while controlling when the data is allowed to change. Here, we're looking at a mux-based latch that uses pass transistors, a common approach in VLSI design. The operation relies on non-overlapping clocks to control the state of the latch. When the clock signal is high, transistor N1 turns on, allowing the input D to pass through directly to the output Q. This means the latch captures the input value during this phase. Conversely, when the clock goes low, transistor N2 switches on, creating a feedback loop that holds or retains the previous output state. This mechanism ensures the data is preserved until the next clock cycle. The key concept is that by carefully controlling these two transistors with non-overlapping clocks, we can reliably store and maintain the data in the latch. Here we have the master-slave or edge-triggered register implemented using transmission gates. When the clock signal is low, transmission gate TG2 is active, allowing the data input D to pass through to node X. At the same time, TG1 is off, preventing other paths from influencing node X. During this same period, TG3 is turned on while TG4 remains off, which closes the feedback loop on the slave latch, effectively preserving its previous value and preventing any changes. This clever arrangement ensures that data is only transferred at specific clock edges, improving timing control and stability in the circuit. Overall, this design is fundamental in VLSI for enabling reliable data storage and synchronization. When the clock signal is high, the slave latch becomes transparent. This means that TG3 turns off and TG4 turns on, allowing the output Q to take the value from node X. Meanwhile, the master latch maintains its value through feedback inverters, ensuring data stability when the clock is low. Now, one key disadvantage of the transmission gate register is that each register contributes a clock load equivalent to 8 transistors. This can significantly increase power dissipation because the clock switches frequently, and driving these multiple transistors consumes more power. To address this, the clock load can be reduced by removing the feedback transmission gate. Instead, feedback can be provided by directly cross-coupling the inverters, as shown in the figure. This modification helps to lower power consumption while maintaining proper functionality of the latch. So, the main takeaway here is the trade-off between maintaining data integrity in the latch and managing power efficiency in the clock network. By optimizing the feedback path, we can achieve lower power usage without compromising performance. Here we have a master-slave edge-triggered register implemented using pass transistors. The key components include the master latch, which operates on the negative level of the clock, and the slave latch, which is positive level triggered. When the clock is high, the slave latch becomes transparent, allowing the output Q to take the value of the inverted signal X, effectively capturing the value of the input D. This master-slave configuration ensures that data is reliably transferred on the clock edge, minimizing timing issues common in sequential circuits. Understanding how the master and slave latches work together is crucial for designing robust VLSI registers. Here, we're looking at the issue of overlapping clocks in VLSI design. Sometimes, due to variations in wire delay, two clock signals can go high simultaneously. When this happens, all the transistors labeled N1, N2, N3, and N4 turn on at the same time. This creates a direct path from the input D to the output Q. As a result, node A receives conflicting values from both D and B, which leads to an undefined or unstable state. To prevent this situation, designers use two non-overlapping clocks, ensuring that the clocks never go high at the same time. This simple but crucial measure helps maintain proper timing and reliable operation of the circuit. Now let's take a closer look at static SR flip-flops, which are fundamental building blocks in digital circuits. These flip-flops are often implemented using NOR gates to create the set-reset function, allowing us to store a single bit of information reliably. This NOR-based set-reset configuration provides a simple yet effective way to control the state of the flip-flop. Understanding how these elements work is especially important in VLSI design, where efficient and dependable memory elements are crucial for creating complex integrated circuits. Here, we are looking at a ratioed CMOS SR latch with an added clock signal. When the clock is high and the S input is set to 1, the output Q discharges to 0, which then turns on transistor M4, making Q go high. Conversely, if the R input is 1 while the clock is high, Q discharges and turns on transistor M2, driving Q high. When both S and R are 0, the latch holds or retains its current state, meaning Q and Q do not change. However, when both inputs are high at the same time, it forces both Q and Q to 0, which is a special condition to note. This behavior is fundamental to understanding the operation of the SR latch in VLSI design, as it controls how data is stored and maintained in circuits. Here we have a multiple threshold CMOS latch, a common structure used in low-voltage static latch designs. The key idea here is to use transistors with different threshold voltages, specifically high VD transistors, to reduce leakage currents when the circuit is in sleep mode. Notice the two sleep signals that control the transmission gates, TG1 and TG2, which help isolate the latch from the clock signal during low power states. This isolation is crucial because it prevents unnecessary switching activity and thus saves power. The clock signal drives the latch during active operation, but when the circuit enters sleep mode, the high threshold voltage transistors limit leakage, improving overall power efficiency. This technique is particularly valuable in VLSI design, where power consumption is a critical concern. Here, we see that certain latch structures struggle to function properly at low supply voltages, which limits how much we can reduce power dissipation. Specifically, the input to the inverter can't rise above the switching threshold when the voltage is very low. To address this, the threshold voltage, or VT, should be lowered, but doing so unfortunately increases sub-threshold leakage power. A good solution to this dilemma is to use multiple threshold devices, which help manage the trade-offs between power and performance. During normal operation or sleep mode, the sleep devices are turned on. When the clock signal is low, the data input is sampled and sent through to the output. On the other hand, when the clock is high, the latch enters hold mode. To support this, an extra inverter is connected in parallel with the low threshold inverter, helping maintain the latch's stable operation during hold mode. This approach allows better control of power dissipation while ensuring reliable functionality at varying supply voltages. Now, let's talk about dynamic latches and registers. These components are crucial in digital circuits for storing and transferring data. Unlike static latches, dynamic latches use capacitive storage, which means they rely on a charge stored on a capacitor to hold information temporarily. This makes them faster and more power efficient, but they require careful timing control to prevent data loss. Dynamic registers build on this concept, allowing us to hold data reliably at specific clock cycles, which is essential for synchronous digital systems. Understanding how these elements work helps us design circuits that balance speed, power consumption, and reliability effectively. To manage complexity, we use dynamic logic circuits that store charge on a capacitor. This capacitor only holds the charge for a limited time because it leaks, so we have to refresh it periodically to maintain the stored value. Looking at how a dynamic latch works, when the clock signal is high, the transistor TG1 is off, and the output Q maintains its current state in hold mode. Then, when the clock signal goes low, TG1 turns on, allowing the input D to be stored on the capacitor C1. This process of alternating between hold and store modes is controlled by the clock signal, ensuring the data is captured and maintained dynamically in the circuit. This approach is crucial for VLSI design because it reduces complexity while still effectively storing dynamic data for short periods, making refresh cycles a key part of maintaining reliable operation. Here, we're looking at a dynamic transmission gate edge-triggered register, which operates based on the clock signal transitions. When the clock is low TG1, the first transmission gate is on, allowing the input data D to be stored at node X. At the same time, the slave latch, controlled by TG2, is in hold mode, causing node Y to float. Then, when the clock signal rises to high, TG1 turns off while TG2 turns on, allowing node Y to sample the stored value from node X. This value is then passed through to the output Q. This mechanism ensures that data is captured precisely on the clock edge, enabling stable and reliable data storage, which is essential for VLSI design. Continuing with the setup time, it's important to note that for node X to become stable, the delay involved is just the delay of a single transmission gate. This means the setup time is relatively short and efficient. The signal then propagates from node X to the output Q through the path I1 to transmission gate TG2, and then to node I3. Regarding hold time, it is 0 in this case because as soon as the clock rises, transmission gate TG1 turns off immediately, preventing any data from changing prematurely. However, if there is any overlap in the clock signals, this could potentially affect the timing and stability of the signals. Understanding these delays and timing behaviors is crucial in VLSI design to ensure reliable circuit performance. Now let's take a closer look at clocked CMOS, often referred to as C2MOS. When the clock signal is low, the master latch becomes transparent. This means that transistors M4 and M3 switch on, allowing node X to take the inverted value of the input. Meanwhile, the slave latch is off and effectively in a hold mode, which means that the output Q retains its previous value without change. This behavior is fundamental in controlling data flow and timing in VLSI design, ensuring that information is accurately latched and propagated within the circuit. Understanding this operation is key to grasping how clocked latches manage data in synchronous digital systems. Here, we're looking at the concept of clock CMOS or C2MOS. The key idea is how the clock signal controls the transparency of the second stage, called the slave. When the clock is high, this slave stage becomes transparent, meaning it allows signals to pass through without alteration. At this point, the output Q receives the inverted value of node X. What this effectively means is that the input D is passed through two stages before appearing at the output Q. This two-stage propagation is a critical aspect in VLSI design, ensuring accurate timing and signal control within the circuit. Here we're looking at clocked CMOS or C2MOS. When both clock signals are low, meaning clock and clock bar are at 0, transistors M4 and M8 turn on, while M3 and M7 turn off. Now, if the input D is low during this time, node X will go to a high state, or 1. But if D is high, node X holds its prior value because transistor M2 remains off. This behavior is crucial for controlling the state retention in the circuit. Understanding how the clocks influence these transistors helps us design reliable VLSI circuits that perform correctly with precise timing. Here, we're looking at clock CMOS or C2MOS, which is a key concept in VLSI design. Basically, if the input D is low, the node X holds its previous value. This happens because M1 is off, so there's no way for the node to charge or discharge. It just stays as it was. But when D goes high, M2 switches on, creating a path for node X to discharge. This selective charging and discharging, controlled by the clock and input, is fundamental in managing state and timing in CMOS circuits, making C2MOS an essential technique in ultra-large-scale integration design. Now let's talk about clock CMOS or C2MOS. The key point here is that in C2MOS circuits, overlapping of clock signals doesn't impact the output. This is an important advantage because it ensures stable operation even when clocks overlap slightly. However, there's a catch. If the clock's rise and fall times are too long, it can create an unintended path between the input and output during that transition period. This can influence the current state of the register, potentially causing errors. So, controlling the clock transition times is critical in VLSI design to maintain reliable performance. Here, we focus on true single-phase clock latches or TSPC latches, which are widely used in VLSI design due to their efficiency. Starting with the positive latch, it's important to note that this latch becomes transparent when the clock signal, CLK, is high. In other words, when CLK is equal to 1, the output directly follows the input. For example, if the input is 0, the output node will also be 0. On the other hand, when the clock goes low, there's no discharge path available in either of the two stages, which helps maintain the stored value. The key advantage of the TSPC latch is its use of a single-phase clock, simplifying timing and reducing complexity. Both positive and negative TSPC latches are implemented by cascading two inverters, making them efficient and easy to integrate within VLSI circuits. This design helps in optimizing the clocking scheme while preserving signal integrity. Here we're looking at true single-phase clock latches or TSPC latches, which are widely used in VLSI design. The key feature of the TSPC latch is that it operates with a single-phase clock. This simplifies timing and control compared to using multiple clock phases. Now focusing on the negative latch, it behaves oppositely to what you might expect. When the clock is low, the latch is transparent, meaning it passes the input through to the output. When the clock goes high, the latch holds its value, effectively storing the data. The way TSPC latches are implemented is quite elegant, by cascading two inverters. This setup creates either a positive or negative TSPC latch, depending on how it's configured, ensuring efficient operation within complex VLSI circuits. This single-phase approach helps reduce clock skew and power consumption, making it highly valuable in modern digital designs. Here we have the TSPC or positive edge triggered register. Let's break down what's happening during the clock cycle. When the clock is low, transistor P2 turns on. This means that node X holds the inverted value of the input D. So depending on D's value, node X can either charge or discharge accordingly. At the same time, the second stage dynamic inverter is in its pre-charge mode because transistor P3 is on, which charges node Y to a high level. In the third stage, the inverter is in hold mode. This happens because both the charging and discharging paths are inactive. Transistors P4 and N4 are off, so the output Q maintains its previous state. This configuration enables the register to reliably latch the data on the positive edge of the clock. Now let's talk about pulse registers, which use a fundamentally different method for building a register. Instead of the traditional approach, pulse registers generate a short pulse right around the rising or falling edge of the clock signal. This pulse essentially acts as the clock input to a latch, allowing it to sample the input only during this very brief window. This short sampling period is key because it helps avoid race conditions by keeping the latch transparent for only a very small amount of time. In other words, the latch only opens momentarily to capture the input data, which enhances timing control and stability. The circuit that combines the pulse generation with the latch creates what's known as a positive edge-triggered register. The diagram, referred to here as Figure B, illustrates how you can intentionally create this short glitch or pulse on every rising edge of the clock, enabling precise timing for the register operation. Here, we're examining the behavior of node X in relation to the clock's signal CLK. When CLK is at 0, node X charges up to the supply voltage, VDD. This happens because transistor MN is off, as the control signal CLKG is low at this time. Then, as the clock transitions from low to high, there's a brief moment when both inputs of the and gate become high. This causes the signal CLKG to go high, triggering the next phase of the operation. This sequence is crucial because it controls when node X is charged or discharged, directly impacting the timing of the circuit. Here, we see how activating MN pulls signals X and CLKG low, as shown in Figure C. The duration of this pulse is determined by the delay introduced by the in-gate and the two inverters. This delay also creates a gap between the rising edges of the input clock, CLK, and the glitch clock, CLKG. When we measure setup and hold times relative to the rising edge of the glitch clock, the setup time effectively becomes 0. The hold time corresponds to the pulse length, assuming the contamination delay is negligible, and the propagation delay, or TCQ, amounts to 2 gate delays. The main advantage of this method is that it significantly reduces the clock load and requires fewer transistors, which simplifies the design and improves efficiency. Now, let's focus on the flow through a positive edge-triggered register. This means that the data input is captured only at the moment when the clock signal transitions from low to high, also known as the positive edge. This is crucial because it ensures that the register updates its stored values synchronously with the clock, providing reliable timing and coordination in digital circuits. By triggering on the positive edge, we prevent any changes during the clock's high period, which helps in maintaining stable and predictable operation. Understanding this behavior is key to designing effective sequential logic systems. Here we see another version of the pulsed register. When the clock signal is low, transistors M3 and M6 are off, and device P1 is turned on. This causes node X to be precharged up to VDD, while the output node Q is decoupled from node X and stays at its previous value. An important point is that CLKD is a delayed and inverted version of the clock's signal CLK. On the rising edge of the clock, M3 and M6 switch on, allowing devices M1 and M4 to remain active briefly. This brief period is controlled by the delay through 3 inverters. During this time, the circuit becomes transparent, effectively sampling the input data D into the latch. When CLKD goes low, node X disconnects from the input D and either holds its value or begins precharging back up to VDD, controlled by PMOS device P2. Finally, on the falling edge of the clock, node X is held steady at VDD, and the output Q remains stable thanks to the cross-coupled inverters. This operation ensures that data is latched correctly and held reliably throughout the clock cycle. Here, we're focusing on sense amplifier-based registers. These registers utilize sense amplifiers to improve speed and power efficiency in reading stored data. The key advantage is that sense amplifiers enable faster data sensing compared to traditional methods, which helps boost overall performance in memory circuits. Understanding how these registers operate is crucial for designing high-speed digital systems with optimized power consumption. Here, we're looking at sense amplifier circuits, which play a crucial role in detecting and amplifying very small differences between 2 input signals. Essentially, they use positive feedback to boost these tiny differences, turning them into full-scale output swings that go from rail to rail. This makes them indispensable in areas like memory cores and low-swing bus drivers, where either performance needs to be enhanced or power consumption minimized. The figure illustrates a design that starts with a precharged front-end amplifier. This amplifier samples the differential input signal on the rising edge of the clock, ensuring precise timing. Then, the outputs from this front-end feed into a NAND cross-coupled SR flip-flop. This flip-flop holds the data stable and guarantees that the differential outputs only switch once per clock cycle, preventing erratic behavior. At the heart of this front end is a cross-coupled inverter pair, labeled M5 through M8. These inverters are pre-charged by devices M9 and M10 during the low phase of the clock, preparing the circuit for the next sampling event. This pre-charging step is vital because it resets the outputs, enabling accurate detection of the small voltage differences when the clock rises again. Overall, this design balances speed and power efficiency very well, which is why it's so widely used in modern circuits. Here, the PMOS transistors M7 and M8 are turned off, which means the NAND flip-flop is holding its previous state. This is important because it maintains the stored value until the next evaluation phase. Transistor M1 acts like an evaluate switch in dynamic circuits and is turned off during the low phase of the clock. This ensures that the differential inputs do not interfere with the output when the clock is low. When the clock rises, the evaluate transistor turns on, enabling the differential input pair M2 and M3. This causes the difference between the input signals to be amplified at the output nodes L1 and L2. Then, the cross-coupled inverter pair flips to one of its stable states based on the input values. For example, if the input IN is 1, then L1 is pulled down to 0, while L2 stays at the supply voltage, VDD. Because of how the input stage amplifies signals, the input doesn't need to swing all the way up to VDD, allowing for low swing signaling on the input wires, which is efficient and reduces power consumption. Now, let's talk about why we need the shorting transistor M4. This component plays a crucial role in our circuit by ensuring that certain unwanted voltage levels are avoided. Essentially, M4 acts to short or connect specific points in the circuit to prevent issues like signal distortion or latch-up conditions. By including M4, we improve the overall stability and reliability of the design, which is vital for maintaining consistent performance under different operating conditions. So, the key takeaway here is that the shorting transistor M4 is necessary to safeguard the circuit and enhance its robustness. Here, we're looking at the role of the shorting transistor, labeled M4. Its main job is to create a DC leakage path from either node L3 or L4 to ground. This is crucial in situations where the inputs change after the positive edge of the clock signal has already happened. When that occurs, one of these nodes can end up in a high impedance state, but still hold a logical low voltage. Without the leakage path provided by M4, leakage currents could slowly charge this node, potentially causing the latch to change its state before the next clock edge arrives. So, the shorting transistor helps maintain the correct state and prevents unintended changes between clock cycles. Now, let's talk about pipelining. Pipelining is a technique used in computer architecture to increase instruction throughput. Think of it like an assembly line in a factory, where different stages of instruction execution are processed simultaneously. This allows the CPU to work on multiple instructions at different stages, improving overall efficiency. It's a crucial concept because it helps modern processors achieve higher performance without increasing the clock speed excessively. Understanding pipelining will give us better insight into how computers manage to execute tasks so quickly. Now, let's talk about pipelining in VLSI design. Pipelining is an approach used to optimize sequential circuits by overlapping different stages of processing, much like how water flows continuously through a pipe without waiting for the previous water to completely exit. This analogy helps us understand how pipelining keeps the data moving smoothly and efficiently through the circuit. It's a widely used technique because it accelerates the operation of data paths in digital processors. Essentially, pipelining improves resource utilization by allowing multiple operations to be processed simultaneously at different stages, which in turn increases the overall functional throughput of the system. This means faster processing and better performance in our designs. Pipelining is essentially a technique where we connect several data processing elements in a series, so the output of one becomes the input of the next. This allows us to feed a continuous stream of data into the system, and it processes this data in a regular sequence, producing outputs one after another efficiently. The key idea behind pipeline design is breaking down a complex sequential process into smaller, manageable parts called stages or segments. Each stage has a specific function and generates an intermediate result before passing it along. Typically, each stage includes an input latch, sometimes called a register or buffer, that temporarily holds data. This latch is connected to a processing circuit, which can be either combinational or sequential. The output of this processing circuit then feeds into the next stage's input latch, creating a smooth, step-by-step flow of data through the pipeline. This structure allows us to improve the throughput and overall performance of data processing systems. It seems this slide is blank or doesn't contain any visible content to discuss. If you could provide more details or the content intended for this slide, I'd be happy to guide you through it. Here, we're looking at the computation time without pipelining in VLSI design. The key formula for the minimum computation time, TMIN, is the sum of several delays: the register propagation delay, adder delay, absolute value delay, logarithm delay, and the register setup time. Specifically, TMIN equals TPDR plus TAD plus TABS plus TLOG plus setupr. In this example, the register propagation delay and setup time are both 1 nanosecond each, while the adder, absolute value, and logarithm delays are each 2 nanoseconds. Adding these together gives us a total minimum computation time of 8 nanoseconds. This calculation highlights how each component's delay adds up directly when pipelining is not used, impacting the overall speed of the computation. Let's take a closer look at the pipeline structure in VLSI design. The key idea of pipelining is inserting registers between logic stages to improve performance. This breaks the circuit into smaller stages, allowing each to process data simultaneously, but at different points in time. The formula for the minimum clock period in a pipeline design is TMIN. Pipe equals the clock-to-Q delay plus the maximum delay among the adder, the absolute unit, and the logic unit, plus the setup time of the register. To illustrate, the given example sets the clock-to-Q delay and the register setup time both to 1 nanosecond. The delays for the adder, absolute, and logic units are each 2 nanoseconds. So, the critical path delay here is 1 nanosecond plus the maximum of 2 nanoseconds from the logic blocks, plus 1 nanosecond setup time, totaling 4 nanoseconds. This calculation shows how pipelining helps by breaking the path into shorter stages and adding registers, effectively reducing the overall cycle time to 4 nanoseconds in this case, which is crucial for higher clock frequencies and better throughput. Here, we are looking at an example to understand the impact of pipelining on the minimum clock period. We are given the propagation delay and setup times, with TPDR and setupr both equal to 1 nanosecond. Additionally, the adder delay, setup delay, and logic delay are each 2 nanoseconds. First, let's consider the case without pipelining. The total clock period required, TOT, is calculated as the minimum clock period TMIN multiplied by 5, because we have 5 sets of inputs processed sequentially. This TMIN is the sum of the propagation delay, TPDR, the adder delay, TAD, the setup delay, TABS, the logic delay, TLOG, and again the setup time, setupr. Adding these together, we get a minimum clock period of 8 nanoseconds. Therefore, the total clock period required without pipelining is 8 nanoseconds multiplied by 5, which results in 40 nanoseconds. This provides a baseline to compare when we introduce pipelining in the next step. Here, we have a table illustrating the pipeline stages for processing 5 inputs through 3 operations: addition, absolute value, and logarithm. Each clock period shows which computations occur concurrently in each stage. For example, in the first clock cycle, only the first addition A1 plus B1 is performed. In the second cycle, the second addition A2 plus B2 happens alongside the absolute value of the previous result. This pipelining continues until all inputs have passed through all operations. From this timing diagram, it's clear that completing the entire sequence for 5 inputs takes 7 clock cycles. We use this to calculate the total pipeline delay, which is the minimum pipeline stage time multiplied by 7 cycles. The minimum stage time itself is calculated by summing a few key elements: the register propagation delay, the maximum computation delay among addition, absolute value, and logarithm operations, and the register setup time. Here, each delay is either 1 or 2 nanoseconds, giving a total minimum stage delay of 4 nanoseconds. Multiplying this by 7 clock cycles gives us the total pipeline time for processing these 5 inputs. This breakdown highlights how pipelining allows overlapping of operations to improve throughput, but the overall time depends on the slowest stage and the number of stages in the pipeline. Here, we're looking at latch-based pipeline circuits, which are crucial in VLSI design for handling sequential data efficiently. When the clock signal is high, the transistor labeled N1 is turned on, enabling C1 to store the input data. Then, at the falling edge of the clock, the logic block F takes that stored data from C1, processes it, and stores the result in C2. Next, when the clock rises again, another logic block, G, samples the data held in C2, performs its operation, and stores the outcome in C3. At the same time, N1 switches back on, ready to capture the next input at C1. This alternating sequence ensures smooth, continuous pipeline operation by overlapping data storage and evaluation phases, which is essential for achieving high-speed processing in VLSI circuits. Here, we are looking at a pipeline data path that utilizes C2 MOS latches. The main reason for using this pipeline C2 MOS design is to overcome race conditions, which can cause errors in timing and data integrity. In this design, the logic block F is evaluated at the falling edge of the clock signal, CLK. Then, at the falling edge of the complementary clock signal, CLK, the logic block G is evaluated, and its output is stored in the C3 latch. An important aspect of this system is that it remains race-free only if the logic functions involved are non-inverting. This means the transitions in the logic must not flip the signal polarity, which helps maintain proper timing and synchronization in the pipeline stages. Overall, this approach helps in VLSI design by ensuring reliable and stable operation of pipeline circuits without race hazards. The NORA CMOS modules are designed by combining C2 MOS pipeline registers with NORA dynamic logic function blocks. Each module includes both a block of combinational logic and a latch, allowing for efficient processing within the circuit. The combinational logic can consist of a mix of static and dynamic logic, providing flexibility in the design. Importantly, the logic and latch are clocked simultaneously, ensuring they are both either in evaluation or hold, which is also known as pre-charge mode. This synchronization is critical for maintaining performance and reliability. Additionally, the NORA data path is structured as a chain that alternates between CLK and CLK modules, creating a balanced and robust timing scheme essential for VLSI design. Here, we focus on the CLK module within the context of VLSI design. The CLK module is crucial because it manages the clock signals that synchronize various components of the chip. Proper clock management ensures that data is processed efficiently and accurately throughout the system. In VLSI design, where millions of transistors operate together, the role of the CLK module becomes even more significant to maintain timing integrity and overall performance. Understanding how this module functions helps us optimize the chip speed and power consumption, which are key factors in advanced VLSI systems. Here, we're looking at non-bistable sequential circuits, which are a bit different from the bistable ones we might be more familiar with. These circuits don't have two stable states. Instead, they rely on one or no stable states. Let's start with the Schmitt trigger. It's a type of circuit that's really useful for shaping noisy or slow signals into clean digital pulses by providing hysteresis. Then, moving on to monostable sequential circuits. These are often called one-shot circuits because they generate a single output pulse in response to an input trigger. Lastly, astable sequential circuits have no stable state at all. They continuously oscillate between states, basically creating a clock or timing signal. Each of these circuits plays a unique role in digital electronics, especially when precise timing or signal conditioning is needed. A Schmitt trigger is a special type of comparator circuit that uses positive feedback. This means that even small changes in the input signal result in significant changes at the output, and these changes happen in the same phase. One of the key features of a Schmitt trigger is its ability to implement hysteresis, which helps to stabilize the output by creating two different threshold voltage levels for switching. This hysteresis is clearly seen in the DC characteristics of the device. Because of this hysteresis, the Schmitt trigger can effectively remove noise from analog signals before converting them into a clean digital code. This ensures that any small fluctuations or disturbances in the input do not cause erratic switching in the output. Additionally, Schmitt triggers are known for their fast transient response, meaning they switch quickly when the input crosses the threshold levels. Overall, their main purpose is to suppress noise and provide a more stable and reliable digital output from noisy analog signals. The Schmitt trigger has two key properties that make it very useful in signal processing. First, it can take a slowly changing input signal and produce a rapid, clean transition at the output. This means it effectively sharpens or cleans up noisy or slow signals. Second, its voltage transfer characteristic is unique because it has different switching thresholds depending on whether the input is increasing or decreasing. This creates a kind of hysteresis, which helps to prevent false triggering due to small fluctuations around the threshold. Understanding these voltage transfer characteristics is fundamental to appreciating how a Schmitt trigger operates in different applications. Here, we see a typical voltage transfer characteristic of the Schmitt trigger. The key feature to note is the presence of two distinct switching thresholds, Vm plus for the low to high transition and Vm minus for the high to low transition. This creates a hysteresis voltage, which is simply the difference between these two thresholds. This hysteresis is crucial because it helps the Schmitt trigger reject noise. Speaking of noise suppression, the main advantage of this device is its ability to convert a noisy or slowly varying input signal into a clean, stable digital output. This makes it extremely useful in situations where signal integrity is vital despite fluctuations or interference in the input. The Schmitt trigger operates using positive feedback, which creates a very sharp, steep output signal. This sharpness is crucial because it helps reduce power consumption by suppressing direct path currents that would otherwise flow continuously and waste energy. Now, when it comes to CMOS implementation of the Schmitt trigger, the switching threshold plays a central role. The threshold is determined by the ratio of the NMOS to PMOS transistor sizes, specifically the Kn/Kp ratio. If we increase this ratio, the threshold voltage decreases. Conversely, reducing the ratio raises the threshold voltage, denoted as Vm. For a practical example, consider the case when the input voltage, Vin, starts at 0. This means the output voltage, Vout, is also 0. Due to the feedback loop, the PMOS transistor M4 remains on, conducting current, while the NMOS transistor M3 stays off. This configuration ensures the proper operation of the Schmitt trigger and highlights how the feedback mechanism influences the transistor states to achieve the desired switching behavior. Here, the input signal is connected to an inverter made up of two PMOS transistors, M2 and M4, arranged in parallel to form the pull-up network, and a single NMOS transistor, M1, as the pull-down device. This setup changes the effective transistor ratio to Km1 divided by the sum of Km2 and Km4, which shifts the switching threshold higher. When the inverter switches state, a feedback loop turns off transistor M4 and activates another NMOS transistor, M3. This additional pull-down transistor helps speed up the output transition, resulting in a clean signal with sharp, steep edges. The overall design optimizes switching performance by carefully controlling transistor operation and threshold levels. Here, we're looking at the high-to-low transition in the circuit. Initially, the pull-down network includes transistors M1 and M3 working in parallel, while the pull-up network consists of transistor M2 alone. This configuration lowers the switching threshold voltage to Vm, which is crucial for the circuit's behavior. One of the main advantages of this setup is its ability to reduce power consumption. It does this by suppressing direct path currents, which are currents that flow directly from the supply to ground and waste energy unnecessarily. Additionally, this design helps clean up input signals that might be noisy or change slowly, converting them into clean digital outputs. This ensures the circuit operates reliably and efficiently. A monostable sequential circuit is designed to produce a single pulse of a set duration whenever it is triggered. It's known as monostable because it has only one stable state, which is the resting or quiescent state. When a trigger event occurs, either a change in the signal or an input pulse, the circuit temporarily shifts into a quasi-stable state. This state is not fully stable, so after a specific amount of time, determined by the circuit's internal components, it returns automatically back to its original stable state. These circuits are often called one-shots because they generate one pulse of a fixed length each time they're activated, making them very useful when you need precise, controlled pulse timing. Here, we're looking at the most common way to implement one-shot circuits, which is by using a simple delay element to control how long the pulse lasts. In the stable or quiescent state, the inputs to the XOR gate are the same, so its output remains low. However, when there's a change or transition on the input, the XOR inputs become different for a brief moment, causing the output to go high. This high output doesn't last forever. After a delay time, which we call TD, this difference between the inputs disappears as the delay element resets things, and the output returns to low. So essentially, this creates a pulse whose length corresponds exactly to the delay TD. The way we build this delay can vary. It could be an RC network or a series of basic logic gates chained together to achieve the desired timing. This approach is simple, but very effective for generating precise pulses. An astable sequential circuit is one that doesn't have any stable states. Instead, its output continuously oscillates between two quasi-stable states. The period of this oscillation depends on factors like the circuit's design, delay characteristics, and power supply. A common example is the ring oscillator. This circuit is made up of an odd number of inverters connected in a loop. Because of the odd number of inversions, the circuit can't settle into a stable point, so it keeps oscillating. The oscillation period is determined by twice the propagation delay per inverter multiplied by the number of inverters. This simple design effectively demonstrates how astable circuits operate by relying on the intrinsic delays in the components to produce continuous oscillations. Here, we're looking at the concept of a ring oscillator, which is essentially a series of inverters connected in a chain. The key point is that the oscillation frequency of this ring oscillator depends on the propagation delay of each inverter, with N representing the number of inverters in the chain, and Tp being the delay of a single inverter. What's important to understand is that the frequency generated by this oscillator is fixed, determined by these delays in the CMOS process. However, many applications require control over this frequency, which is where the voltage-controlled oscillator, or VCO, comes into play. A VCO is a circuit whose oscillation frequency varies as a function of a control voltage. Typically, this relationship is nonlinear. To convert a standard ring oscillator into a VCO, we replace the usual inverters with what's called current-starved inverters. This modification allows us to control the delay time of each inverter. The way this control works is by limiting the current that can discharge the load capacitance of the gate. By restricting this current, we effectively control how long each inverter takes to switch, which in turn controls the overall frequency of the oscillator. This approach is crucial for fine-tuning signals in many electronic systems. In this modified inverter circuit, we control the maximum discharge current by introducing an additional series device. This helps prevent the current from going too high, which can improve the circuit's reliability and performance. To manage the low-to-high transition, a PMOS device is added in series with the transistor M2. This addition gives us more control over how the inverter switches back to a high state. Moreover, there's an NMOS transistor labeled M3, which is controlled by an analog voltage called VCNTL. By adjusting VCNTL, M3 effectively reduces the discharge current, which leads to an increase in the propagation delay time, TPHL. This controlled delay can be crucial in applications where precise timing is needed. Overall, these modifications enhance the inverter's switching characteristics by carefully regulating current flow and transition timing. Here, we're looking at how adjusting the propagation delay in each stage of a ring oscillator lets us control its frequency. This is usually done by setting a control voltage through feedback, which helps fine-tune performance. However, when operating at low current levels, the current-starved inverter experiences slow fall times at its output, leading to noticeable short-circuit current, which isn't ideal. To address this, we feed the output into a CMOS inverter, or even better, a Schmitt trigger. This approach improves signal integrity and speed. Additionally, we include an extra inverter at the end to ensure the oscillator continues to function properly, maintaining stable oscillations. It seems there is no content provided for this slide. Could you please share the specific details or text that you would like me to cover in the narration? This will help me create an effective and engaging script for you. Now, let's focus on the differential delay element. This component is crucial because it introduces a controlled time difference between signals. By doing so, it allows us to analyze how variations in timing influence the overall system performance. Understanding this element helps us manage signal alignment and detect timing discrepancies, which can be vital in applications requiring high precision and synchronization. It's essentially a building block for maintaining timing accuracy within complex signal processing setups. Here, we're looking at an alternative way to implement a delay element by using a differential element, as illustrated in Figure A. This delay cell is versatile because it provides both inverting and non-inverting outputs. Thanks to that, you can build an oscillator with an even number of stages, which is not typically straightforward. Moving on to Figure B, this shows a practical example, a two-stage differential VCO. The key here is the feedback loop, which introduces a 180-degree phase shift. It achieves this through two gate delays, one inverting and the other non-inverting, creating the necessary conditions for oscillation. Finally, Figure C presents the simulated waveforms for this two-stage VCO. Notice that it simultaneously produces outputs that are in phase and in quadrature phase, which is particularly useful for applications requiring these signals in parallel. This setup highlights how the use of differential delay elements can effectively simplify designing even-stage oscillators. Here, we're looking at the advantages and disadvantages of the differential-type voltage-controlled oscillator, or VCO. One key advantage is its improved immunity to common mode noise, which makes it more reliable in noisy environments compared to a common ring oscillator. However, this comes with a trade-off. The differential VCO consumes more power because of its increased complexity and the static current it requires. So while it performs better in terms of noise rejection, it demands greater power consumption. Now, let's focus on timing issues in sequential circuits. Timing is crucial in these types of circuits because they rely on the precise sequencing of signals to function correctly. Any delays or mismatches in timing can cause errors, such as incorrect data being stored or propagated. Factors like setup time, hold time, and clock skew play significant roles in ensuring that data is captured at the right moment. Understanding and managing these timing constraints is essential for designing reliable and efficient sequential circuits. Let's begin by discussing the timing classification of digital systems. This is a fundamental concept that helps us understand how digital circuits operate with respect to time. Timing classification essentially divides systems based on how they handle timing signals or clocks. This classification is crucial because it affects the design strategy we choose and the overall performance of the system. Next, we focus on synchronous design, which is a common approach in digital systems. In synchronous design, all changes in the system are coordinated by a clock signal. This clock ensures that all parts of the circuit update their states simultaneously, which greatly simplifies the design and timing analysis. By using a clock, synchronous systems achieve reliable and predictable behavior, making them easier to test and debug. These 2 points, timing classification, and synchronous design are key to understanding how digital systems function and how we can effectively design them. Timing classification provides the framework, and synchronous design is one of the most widely used implementations within that framework. In digital systems, the way signals behave in relation to a local clock helps us classify them into different categories. Essentially, signals that change or transition only at specific, predetermined times based on the system clock fall into a few key types. First, we have synchronous signals, which are tightly coordinated with the clock, ensuring all parts of the system change state simultaneously. Then there's mesosynchronous signals, which share the same clock frequency but might have different phases. Plesiochronous signals are almost synchronized, but slight differences in their clock frequencies can cause timing variations. Finally, asynchronous signals don't rely on the system clock at all and change independently, which introduces a different set of challenges and design considerations. Understanding these classifications is crucial for designing reliable digital systems. Here, we're talking about synchronous interconnects. What this means is that the signal we're dealing with operates at the same frequency as the local clock, and it maintains a fixed, known phase relationship with that clock. Because of this synchronization, the timing of the signal is predictable and stable. This is crucial because it allows us to sample the data directly without worrying about timing uncertainty, which ultimately leads to more reliable and accurate communication within the system. The key takeaway is that synchronous signals are tightly coordinated with the clock, making data transfer straightforward and dependable. In digital logic design, synchronous systems are the simplest and most common type of interconnect. The key idea is that data flows through the circuit in perfect coordination with the system clock. Here, you can see that the input data signal, labeled in, is first captured by register R1. This step is crucial because it converts the input into a signal, CIN, that is synchronized with the clock. Once synchronized, this signal moves on to the combinational logic block. After allowing enough time for the logic to process the data, the output, COUT, becomes valid. Finally, register R2 samples this output, ensuring that the result is also aligned with the system clock. This entire process guarantees that data moves through the system in a controlled and predictable manner, minimizing timing issues. Here, we're looking at mesosynchronous interconnects. The key idea is that a mesosynchronous signal shares the same frequency as the local clock, but its phase offset is unknown. This situation often arises when data moves between two different clock domains. Although the clocks run at the same frequency, the phase relationship between the transmitting and receiving clocks may not be aligned. To handle this, we use a mesosynchronous synchronizer. This synchronizer adjusts the phase of the incoming data signal to align it with the receiving clock. By doing so, it ensures the data is sampled correctly, preventing timing errors and data corruption. Essentially, the synchronizer bridges the phase gap, enabling reliable communication between the two domains. It seems that this slide is empty or missing content. Could you please provide the text or main points that should be covered on this slide? That way, I can create a clear and effective narration for you. Here, we see that the signal D1 is synchronous with respect to CLK, meaning they share the same timing reference. However, when we look at signals D1 and D2 in relation to CLKB, they are mesosynchronous. This means there is an unknown phase difference between CLKA and CLKB, as well as an unpredictable delay caused by the interconnection between Block A and Block B. This is where the synchronizer plays a critical role. Its job is to adjust a variable delay line so that the data signal D3, which is essentially a delayed version of D2, aligns properly with Block B system clock, CLKB. The adjustment happens by measuring the phase difference between the received data signal and the local clock. Once register R2 samples the data during a period when timing is certain, the output signal D4 becomes fully synchronous with CLKB. This process effectively resolves the uncertainties and ensures reliable data transfer between the two blocks. Here, we're discussing plesiochronous interconnects. A plesiochronous signal has a frequency that is nominally the same as the local clock, but there's a slight difference. Because of this small mismatch, the phase difference between the two signals drifts over time. This usually happens when two modules communicate, but each uses its own independent clock derived from separate crystal oscillators. As a result, the transmitted signal may arrive at the receiving module at a slightly different rate than the local clock expects. To handle this, we need to implement buffering schemes that can accommodate these differences and ensure that all data is properly received without loss or misalignment. This concept is critical in systems where precise synchronization isn't guaranteed, but reliable communication must still be maintained. Here, we're looking at a type of interconnect that you usually find in distributed systems, especially those used for long-distance communications. Unlike chip or board-level circuits, which generally rely on a shared oscillator to generate local clocks, these interconnects don't have that luxury. This means the timing has to be managed differently, which can introduce unique challenges, but is necessary for maintaining synchronization over longer distances. Understanding this distinction is key to grasping how distributed systems handle communication effectively. In this digital communications framework, the originating module sends data at a rate denoted by C1, which is plesiochronous, meaning it's almost but not exactly synchronized with another clock, C2. To handle this, the timing recovery unit extracts a clock, called C3, directly from the incoming data stream. This clock C3 aligns perfectly with the data as it enters the FIFO buffer, making it mesochronous with C1, which means they share the same frequency but may have a phase difference. Since the clocks from the originating and receiving modules don't match perfectly, we might face situations where data has to be dropped if the transmitting frequency is higher, or sometimes duplicated if it's slower. The key to managing these differences is to have a sufficiently large FIFO buffer. By doing this and resetting the system whenever an overflow occurs, we ensure that communication remains robust and reliable despite the clock mismatches. Here we are looking at asynchronous interconnects. Unlike synchronous signals that are tied to a local clock, asynchronous signals can change at any random time. They're not controlled by any clock signal. This makes it challenging to convert these unpredictable transitions into a neat, synchronized data stream. One common approach to managing this is to detect specific events within the asynchronous signal and then introduce some delay or latency, so that the data can be aligned with a local clock. Essentially, this tries to bring the asynchronous data into the synchronous domain by adding timing buffers. However, a more elegant solution is to avoid using local clocks altogether. Instead, you can adopt a self-timed asynchronous design. This means the system regulates itself without relying on a global clock, allowing it to handle asynchronous signals naturally and efficiently. This approach can simplify timing issues and improve robustness in some circuits. Here, we're looking at a communication method between modules that relies on a handshaking protocol. Essentially, this protocol ensures that commands are executed in the correct order. By controlling the interaction through these handshake signals, each module knows when to send or receive data, preventing errors and maintaining synchronization. This orderly exchange is crucial for reliable system performance. When a logic block finishes its operation, it sends out a completion signal called DV. This signal tells the next part of the system that the output data is ready and valid. At this point, handshaking signals come into play to manage the data transfer smoothly. The next block receives this data, latches it in, and then starts its own computation by sending an initialization signal, marked as I. This process ensures that each block communicates effectively and the data flows seamlessly through the system. Asynchronous designs offer several advantages that make them quite appealing. First, computations happen at the native speed of each logic block, meaning each part works as fast as it can without waiting for a global clock. This allows computations to occur whenever data is ready, enhancing efficiency. Another benefit is that there's no need to manage clock skew, which simplifies timing issues often encountered in synchronous systems. The design approach is also very modular, with blocks interacting through a handshaking protocol, which makes the system easier to scale and maintain. However, there are some drawbacks. The main disadvantage is the increased complexity and overhead involved in communication between blocks. This extra overhead can sometimes reduce overall performance, so it's important to weigh these trade-offs when considering an asynchronous design. Now, let's dive into synchronous design and some of the key challenges it presents. One major issue we face is synchronous timing, which essentially revolves around making sure all parts of a system are perfectly coordinated with a clock signal. Two common problems here are clock skew and clock jitter. Clock skew happens when the clock signal arrives at different components at slightly different times, which can cause timing errors. Clock jitter, on the other hand, is the small, rapid variations in the clock signal itself, which can also disrupt timing accuracy. To manage these issues, we use various clock distribution techniques designed to deliver reliable, consistent clock signals throughout the entire system. Understanding and addressing these concepts is crucial for maintaining performance and stability in synchronous designs. Today, most systems are designed to work with a periodic synchronization signal, commonly known as a clock. This clock plays a crucial role because how it's generated and distributed can greatly affect both the system's performance and power consumption. In positive edge-triggered systems, the rising edge of the clock essentially marks the start and end of each clock cycle. If we look at a synchronous pipeline data path, the ideal scenario is that the clock's driving registers 1 and 2 have identical periods and switch states simultaneously, ensuring smooth and reliable data transfer between stages. This precise timing coordination helps prevent errors and optimizes system efficiency. It seems like this slide is blank or doesn't contain any content for us to discuss. If there's supposed to be material here, please let me know or provide the content, and I'll be happy to walk through it with you. Otherwise, we can move on to the next slide. In sequential circuits, timing parameters are crucial for ensuring proper operation. First, we have the contamination delay, often called the minimum delay, denoted as TCQ-CD, which relates to the register's behavior. Alongside this, the maximum propagation delay of the register, TCQ, sets an upper bound on how long signals take to pass through. Next, we consider the setup time, TSU, and the hold time, fold, for the registers. These are critical intervals around the clock edge where input data must be stable to be correctly registered. Moving on to the combinational logic, we again have contamination delay, tlogic, CD, and maximum delay, tlogic, which indicate the fastest and slowest time signals can propagate through the logic circuitry. Lastly, the timing of the clock edges themselves, specifically the rising edges of CLK1 and CLK2, noted as TCLK1 and TCLK2, are measured relative to a global reference point. This timing relationship is essential for synchronizing the entire sequential system accurately. Understanding these parameters helps us design reliable circuits that function correctly within their timing constraints. In ideal conditions, where the clock periods TCLK1 and TCLK2 are equal, the worst-case propagation delays set the minimum clock period necessary for this sequential circuit to function correctly. Essentially, the clock period must be long enough to allow data to travel through the registers and the logic, and then be properly set up at the destination register before the next clock edge. Mathematically, this requirement is expressed as T being greater than the sum of the clock-to-Q delay, the logic delay, and the setup time. Simultaneously, the hold time constraint ensures the destination register holds the data correctly. The hold time must be less than the minimum propagation delay through the logic network. This means the hold time is constrained by the difference between the clock-to-Q delay and the logic delay at the destination. However, this analysis assumes an ideal clock, which is rarely the case in real systems. Process variations and environmental factors cause spatial and temporal variations in the clock signal, making the timing constraints more complex in practice. These real-world variations must be accounted for to ensure reliable circuit operation. Now, let's talk about some major challenges we face in digital circuits, especially in VLSI design. Two critical issues are clock skew and clock jitter. Clock skew occurs when the clock signal arrives at different components at slightly different times, which can cause synchronization problems. On the other hand, clock jitter refers to the variability or instability in the timing of the clock signal itself, which can lead to errors in data transmission and processing. Understanding and managing these timing issues is crucial for designing reliable and efficient digital circuits. Let's talk about clock skew, a critical concept in synchronous circuits. Clock skew happens when the clock signal reaches different registers at slightly different times. This timing difference can affect circuit performance and reliability. There are two main types of clock skew, positive and negative. Positive clock skew occurs when the clock arrives later at the receiving register compared to the launching register. Essentially, this delay can sometimes be beneficial because it can give extra time for data to propagate, reducing timing violations in certain cases. Negative clock skew, on the other hand, happens when the clock arrives earlier at the receiving register, which can tighten timing margins and potentially cause errors. Understanding the impact of clock skew is vital in VLSI design since it directly influences how reliably your circuit operates at high speeds. Managing clock skew ensures data is transferred correctly between registers without timing errors. The table here summarizes key parameters like clock timing and delay, which help designers analyze and mitigate clock skew effects in their circuits. Here, we're looking at a situation that happens during data transmission between registers in a VLSI design. Specifically, this timing issue occurs when the transmitting register receives the clock signal before the receiving register does. This means the first register might send data too early, before the second register is ready to receive it, which can cause errors or glitches in the data transfer. Understanding this timing difference between clock 1 and clock 2 is crucial for ensuring reliable communication within the circuit. It's a key concept that helps us design more robust systems in VLSI. Here we're looking at the race problem, which is a common issue in VLSI design. Essentially, a race occurs when the sampling of data isn't done correctly. To prevent this, the minimum propagation delay through the register and the logic must be greater than the sum of the clock skew and the hold time. This ensures that data has enough time to settle before being latched. Two important concepts here are the contamination delay of the register and the contamination delay of the logic. These delays impact how quickly signals begin to change after a clock edge, and managing them properly helps avoid race conditions in the design. It looks like this slide is blank or missing content. Could you please provide the details or the text you want me to narrate for this slide? Negative clock skew happens when the clock signal arrives at the receiving register earlier than it does at the transmitting register. This timing difference can impact how data is latched and propagated through the circuit. Essentially, if the clock reaches the receiving register too soon, the data might not be stable or ready, leading to potential timing violations. This contrasts with positive skew, where the clock signal arrives later at the receiver than at the transmitter. Understanding these skews is crucial in VLSI design because they affect setup and hold times, influencing the overall reliability and performance of the circuit. Managing clock skew helps ensure that signals are synchronized correctly and that data transfers happen without errors. Clock jitter is essentially the variation in the timing of a clock signal, meaning the clock period can either lengthen or shorten from one cycle to the next. It's important to understand that jitter is purely a measure of timing uncertainty at a specific point on the chip. We often describe it as the temporal variation in the clock period, and because it's random, it fluctuates around a zero mean value. Now, when we talk about absolute jitter, we're referring to the worst-case deviation of the clock edge compared to an ideal, perfectly periodic clock edge. This worst-case value shows the maximum timing uncertainty you might encounter at that particular point in the circuit. Understanding and managing jitter is crucial because it can affect the reliable performance of high-speed digital designs. Cycle-to-cycle jitter describes the variation in the duration between consecutive clock periods at a specific location. Essentially, it measures how much one clock cycle deviates from the next compared to the ideal nominal clock period. The formula captures this by subtracting the nominal clock period from the difference between two successive clock cycles, Tn plus 1 and Tn, Understanding this helps us identify timing inconsistencies that can affect the overall performance and reliability of a system. Jitter has a significant effect on the performance of sequential systems by introducing variations in the clock period. Ideally, the clock period begins at one edge and ends at another, maintaining a consistent nominal period, which we call TCLK. However, jitter causes the clock edges to shift unpredictably. In the worst case, the rising edge that starts the current clock cycle is delayed, while the rising edge starting the next cycle happens earlier than expected. This effectively reduces the available time to complete operations by twice the jitter amount. To ensure proper operation, the clock period minus twice the jitter must still be long enough to accommodate the clock-to-cue delay, the logic delay, and the setup time. This relationship ensures that the inequality TCLK is greater than or equal to the sum of these delays plus twice the jitter is satisfied, maintaining system stability despite the timing variations caused by jitter. When we talk about sources of skew and jitter in VLSI design, it's important to understand that these issues arise mainly because of a variety of process and environmental variations. Clock skew and jitter essentially happen due to inconsistencies that affect the timing of the clock signal. Some of the key sources include the clock signal generation itself. If the clock isn't generated precisely, that can introduce timing errors. Then there are manufacturing device variations. These are differences that occur during the fabrication process of the chips, which can lead to inconsistencies in how signals propagate. Interconnect variation is another critical factor, as differences in wiring lengths or materials can cause delays or unpredictable changes. Environmental variations like temperature fluctuations or voltage changes can also impact the clock stability. Lastly, capacitive coupling, where signals interfere with each other due to close proximity, can introduce additional noise, leading to jitter. All these factors together contribute to the overall challenge of maintaining a clean, synchronized clock signal in VLSI systems. Understanding these sources helps us design more robust solutions to minimize skew and jitter. When dealing with clock distribution techniques, it's crucial to carefully manage clock skew and jitter because these factors can significantly limit the performance of digital circuits. Minimizing both skew and jitter is essential for a reliable and efficient clock network design. Another important aspect is power dissipation. In high-speed digital processors, the clock network is typically where most of the power is consumed. To address this, clock networks are designed to support clock conditioning, which means they can selectively shut down parts of the network to save power. However, it's important to note that while clock gating helps reduce power, it also introduces additional clock uncertainty. So, balancing power efficiency with timing accuracy is a key challenge in clock distribution design. Now, let's talk about some effective techniques to reduce clock skew and jitter in VLSI design. One common method is the use of an H-tree clock distribution network. This structure helps deliver the clock signal evenly across the chip, minimizing delay differences between various parts. By organizing the clock paths in a symmetric tree-like layout, the H-tree balances the timing so that all sections receive the clock signal simultaneously, which is crucial for synchronized operation. Reducing skew and jitter enhances the overall performance and reliability of the VLSI circuits.